Okay, I'm going to start the integral test here, and in the next couple of sections, we're going to see a whole slew of tests for determining if a series is convergent or divergent. Okay, and just to kind of highlight the introductory paragraph in 11.3 here, in general, it is difficult to find the exact sum of a series. Okay, now you were able to accomplish this for geometric series and some of the telescoping series in the last section. So here was a telescoping series that we looked at in the last section. We were able to find out what it converged to, and then also the same thing is true with the geometric series. We had a formula here, a divided by 1 minus r, and if it was convergent, we could find out what it converged to. Okay, but it's usually going to be very difficult to discover a formula. But so we're not really interested in what it converges to, but that it converges, okay, or just that it diverges. Okay, so that's kind of the main thing with these next couple of sections. So we're going to see a bunch of series, and then does the series converge or diverge? Okay, now just like in chapter 11, or excuse me, chapter 7, when we were looking at the integration techniques, after we did the integration techniques, we then kind of put all that information together, and now they just gave us an integral, and could we figure out which technique to use? Okay, the same sort of deal is going to happen here. So when we get into section 11.8, or excuse me, 11.7, they're going to kind of put all that together, and they're not going to tell us, okay, use the integral test or use the geometric series, to find the value there, okay, or to see if the series converges or diverges. So okay, but let's start to 11.3 here, the integral test. And it says that if f is a function, if f is positive, continuous, and decreasing on the interval 1 to infinity, and a sub n is equal to f sub n, f of n, and then the series given by the summation as n equals 1 to infinity of a sub n is a sequence, and the integral going from 1 to infinity of fx dx, these two things either both converge or both diverge. Okay? Now there's three conditions that have to be met before you set up an integral. Okay? Now, like I said, it kind of when we get into 11.7, they're gonna just give us any series, and we have to identify which form to use there, and then use it to check if the series converges or diverges. Okay, now if the sequence part looks like it belongs in an integral, like usually if you can get like a value, like if it was an integral, in just a couple of steps, maybe use substitution or something like that, then it probably will be an integration technique, or we're using the integral test there. Okay, so like in this first example, what if I had the series given by the sum as n equals 1 to infinity of 1 divided by n squared plus 1? Okay, I want to know, does that series converge or diverge? Well, I need to check that these three conditions happen for using the integral test. Okay, so condition 1 is the sequence part, like positive on the interval. Here we're on the interval 1 to infinity, and yeah, we're going to be positive for all values of n on the interval 1 to infinity. We're also continuous everywhere, but we're going to be continuous on the interval 1 to infinity. Okay, and then are we decreasing on the interval 1 to infinity? Okay, well, to check that, I'm using the first derivative test there, and Just if I let f of x be 1 divided by x squared plus 1, f prime of x would be negative 2x divided by x squared plus 1 squared by using the quotient rule there. Okay, now this is going to be less than 0 whenever the numerator is a positive, right? Because the numerator is always going to be a negative as long as x is a positive number. And the denominator will always be a positive no matter what. Okay, so you'll have a negative divided by a positive. That's going to give you some negative result as long as x is positive. Okay, yeah, so you're going to be decreasing actually on the interval 0 to infinity. Here, we're on the interval 1 to infinity. So we're going to be decreasing there as well. Okay, so in other words, I can use the integral test if I want to here for this. So I verified these 3 conditions happen. And of course, I'm going to use it. So let's see, we got the integral going from 1 to infinity of the function 1 divided by x squared plus 1 dx. Okay, well, that's an improper integral, so I have to use the limit definition. Make sure that you use the limit definition always whenever you have an improper integral. Okay, so we got the limit as t approaches infinity of the integral going from 1 to t of 1 over x squared plus 1 dx. Okay, now that is the antiderivative of tangent inverse. Okay, so I'm going to have the limit as t approaches infinity of tangent inverse of x, and I'm going from 1 to t, and plug in the bounds there. So I have the limit as t approaches infinity of tangent inverse of t minus the limit as t approaches infinity of tangent inverse of 1. Tangent inverse of 1, well, let's see. So tangent of what angle gives me 1, in other words? Well, it's going to be tangent of pi over 4, right? Because the opposite and the adjacent sides are both 1. So pi over 4. Okay, I'm subtracting pi over 4 there. And so now, as t is approaching infinity, tangent inverse of t is going to be getting closer and closer to pi over 2. Okay, that's the graph with 2 horizontal asymptotes on it. I got one at pi over 2, and then another at negative pi over 2, and the curve is going through quadrants 1 and 3. So as I head outward towards infinity, I'm going to be getting closer and closer to pi over 2. Okay, minus the limit of a constant is always the constant. Pi over 2 minus pi over 4 is pi over 4. Okay, so I get pi over 4. Now, that is a finite number, so that tells me that this integral converges. The series also converges. Okay, the integral converges to pi over 4. Now, I've got a note here. Since the integral converges to pi over 4, that does not mean that the series given by the sum as n equals 1 to infinity of 1 divided by n squared plus 1 converges to pi over 4 also. It just means that the series converges. Okay, remember the kind of the note that I read you at the beginning here. So in general, it's very difficult to find out what a series converges to. Okay, so in the next couple of sections here, all we're going to know is, does the series converge or diverge? Okay, but not necessarily what it converges to. We don't really care about that, like unless it's a geometric series or a telescoping series or something like that. Okay, that we've already looked at in section 11.2. Okay, let's try another one here. So I got the summation as n equals 1 to infinity of n divided by n squared plus 1. Okay. Does that series converge or diverge? Well, let's see. So I got to verify. I'm going to use the integral test, and I got to verify that I can use that test first. So f is positive, continuous, and decreasing. Okay. I'm going to have a positive function here, x divided by x squared plus 1. That's positive for all values on the interval 1 to infinity. I'm going to be continuous everywhere. So I'll be continuous on the interval 1 to infinity. And am I decreasing on the interval 1 to infinity? Well, so I'm going to use the first derivative test again here. And here's the function, f of x equals x divided by x squared plus 1. F prime of x, using the quotient rule, that's the bottom times the derivative of the top, minus the top is x, times the derivative of the bottom is 2x, all over the bottom squared. X squared minus 2x squared is negative x squared. It's like 1 minus x squared up top, divided by x squared plus 1 squared down under. Okay, now that is going to be less than 0 whenever x is bigger than 1. Okay, so if x is in between negative 1 and 1, then you'll have the sign will be flipped. But if x is 2, I've got a negative up top. Now the denominator is always going to be positive no matter what. Okay, so as long as x is bigger than 1, then f prime is going to be negative. Okay, and that means that the function is going to be decreasing on the interval 1 to infinity. Okay, and so let's see, that's the third thing that I got to check for it. Now, again, why I'm checking for these is if I can use the integral test. So if one of those conditions does not happen, if one of these does not happen, I can't use the test. And I got to find out some other test to use to see if the series is convergent or divergent. Okay, so it has to satisfy all three of these conditions in order for you to use the integral test. So we can use the integral test here. We got the integral going from 1 to infinity of x divided by x squared plus 1 dx. And that's a u substitution, that problem. If I let u be the denominator, x squared plus 1, du is 2x dx, 1/2 would come out of the new integral involving u. Okay, now I need to use the limit definition here. Okay, so I got 1/2 times the limit as t approaches infinity of 1 over u du, and I'm going from 2 to t. Okay, so that is equal to 1/2 times the limit as t approaches infinity of the ln of the absolute value of u going from 2 to t. And so then when I plug in my bounds here, I got 1/2 times the limit as t approaches infinity of the ln of the absolute value of t minus the ln of the absolute value of 2 is 2, right? So let's see, t is approaching infinity, so the ln of t, that is going to be approaching infinity. Now, I'm subtracting the ln of 2, so what? I'm dividing by 1/2, or dividing by 2, so what? I'm still going to be, getting results that are growing without a bound. Okay, so the end result of that is infinity. And because the integral was divergent, okay, we got infinity there, and that means that the series is also going to diverge. Okay, so the series given by the sum as n equals 1 to infinity of n divided by n squared plus 1 diverges. Okay, now these two series look very similar. Okay, I have n up top, down here, and they just the slightest little change can drastically affect everything with this stuff. Okay, so yeah. All right, why don't we go ahead and stop right there in the notes, and I'll pick up with the what's called the P series test in the next video there. Okay.